Hello, I'm Walker Khan, and this is Lab 3, Magnetic Field of a Bar Magnet. The purpose of this lab is to calculate the magnetic field of a small bar magnet. Bucevar's law aids us in accomplishing this so that we can measure the strength of a magnetic field, given a distance. More specifically, we want to find the distance dependence of a magnetic field due to a bar magnet. To do this, we devised a model as seen on the bottom left to detect magnetic field variance on and off axis. Afterward, we want to develop a computational model that illustrates the forces at play from our input. Bucevar's law measures the intensity of a magnetic field given the magnetic dipole moment, in the case of this experiment, of a point charge. Next is the equation that measures the distance dependence of a bar magnet, which calculates the strength of a magnetic field when provided with a distance, and vice versa. A few assumptions had to be made while carrying out the calculations. We assume that the bar magnet itself is a magnetic dipole and that no external magnetic fields influence the observation position. We also assume that the net magnetic field of Atlanta, Georgia is approximately 49 microteslas. Finally, more is a statement than an assumption. We have to compensate for the Earth's magnetic north. More details on this later. Shown here is the inputted data of the on-axis measurements. To the right is the average distances and strengths of magnetic fields along the x-axis. We find that they range from 20 to 200 microteslas. To the bottom left is the outputted graph and trendline equation. They represent the inputted data seen on the right. The trendline equation that accommodates this graph will play a critical role in future calculations. Here's the data for the off-axis measurements. This temporarily builds off the on-axis model, to which we find the perpendicular distances where our net magnetic field is approximately 100 microteslas. Back to the aforementioned trendline equation. The slope is the distance dependence of our bar magnet. The y-intercept will help us find the magnetic dipole moment through the distance dependence and Bucevar's law equations. We ultimately find the distance dependence to be negative 2.81 meters, while the magnetic dipole is 3.15 amp-meters squared. Here's the glow script code that helps visualize the forces acting within our model. The variable μ_mag is the magnetic dipole moment we calculated earlier. Other important factors include the block of code stating the supplemental vectors forces acting within our system, alongside this block which calculates the strength of the magnetic field for each vector and outputs accordingly. Our code finishes by printing and displaying the 45-degree magnetic field vector. To the right is the output of the glow script code. What lies at the origin represents the bar magnet. The orange arrows represent the on-axis magnetic fields, the blue arrows represent the perpendicular magnetic fields, and the magenta arrow represents the 45-degree magnetic field. Printed on the bottom are the magnetic field vectors for each arrow, finishing off with the perpendicular distance and the value for the 45-degree magnetic field vector. When comparing the value of the 45-degree magnetic field vector, we see that the x components are similar, though the y and z components have a significant range from their counterparts. In terms of the y components, external magnetic fields, such as those within our phones or table, may have caused a difference between experimental and calculated values. The reason why the experimental z component is not equal to 0 when compared to its calculated counterpart may be due to the bar magnet being positioned in 3 dimensions. Knowing this, we may conclude that the distance dependence is negative 2.81 meters, whereas the magnetic dipole moment is 3.15 amps-meters squared. What if we didn't compensate for the magnetic north? How will that affect our results? We will have a different value for the x components of our magnetic field. More specifically, it will have a greater magnitude when compared to our original vector x component. What if we ran this experiment with two identical magnets stuck together? How will that affect the results? If this were the scenario, superposition indicates that the magnetic field will at most double in magnitude. Thanks for watching.